Hello and welcome to the video for lecture 15 where we're going to cover sections 5.4 and 5.8. All right, and we're going to cover these sections because they address the topic of energy conservation and dissipative forces. Okay, so essentially looking at energy but where there's friction. All right, that's the topic here. Okay, and that means we need to define something called a non-conservative force. All right, what is a non-conservative force? Well, it's basically forces like friction. Right? Most of the time when we have a problem that has a non-conservative force, you should just think friction. It can also be air resistance or drag or something, but it's always going to kind of operate like friction. Or maybe it's just a generally called a non-conservative force to be more vague. Okay? But what is it? Well, it's any force that removes mechanical energy from a system. So we talked about mechanical energy in previous lectures, defined how a mechanical energy is always conserved in an isolated system and how isolated systems don't have friction. Well, now we're going to talk about systems that do have friction, that aren't isolated, and where mechanical energy is not conserved. And that might seem like, oh, we're just breaking all the rules, into the story. But actually, as long as we keep things relatively simple, we can use a lot of the same techniques that we used for mechanical energy conservation and just account for the friction. As simple as that. All right, we just kind of add one more term. All right, so such a force converts mechanical energy to heat in most cases. That's where the energy is going. Okay, we're not talking about heat in this chapter yet, but that's kind of foreshadowing things to come. Okay, this also sets the ground or sets the stage for a big idea called the law of conservation of energy. Notice this is different than the principle of the conservation of mechanical energy. And those two terms, principle, law, kind of interchangeable. Law just sounds a little bit more serious. So the law of conservation of energy is one of the three big conservation laws. Okay, we'll talk about the other two, but I won't tell you what they are now. But that's kind of maybe the best way to think about it, because we really do want to always have those three big conservation laws in mind once we've got to those chapters. Okay, but for now, what is the law of conservation of energy? Well, it's a general statement that says energy cannot be created or destroyed, but can only change forms. All right. So all those other types of energy that I mentioned in previous lectures that we certainly aren't talking about yet, like electromagnetic energy, heat energy, nuclear energy. Well, it turns out that you can have systems where all those types of energy are at play, but no energy is created or destroyed. It's just moving from one type to another. Okay, all right. Nuclear energy can become kinetic energy, even quite frequently, in fact. So I mean that's the idea. It really cannot be created or destroyed. All right. Okay. Well, let's get back to talking about mechanical energy plus friction, because that's where we're really at content-wise. Let me zoom in on these equations a bit. Okay, so this right here is just the way we write work done by a non-conservative force. The subscript NC stands for non-conservative, all right? And notice what it's equal to. It's equal to a change in kinetic energy plus a change in potential energy. So in other words, we could write it as the work done by the non-conservative force is equal to a change in mechanical energy. Because that's the thing, before, mechanical energy was a constant, okay? It was a constant when the system was an isolated system. But if we introduce a non-isolated system and have a non-conservative force, well, the whole idea is now mechanical energy can change, but that change is exactly quantified. It's quantifiable. It's just equal to the work done by the non-conservative force. Now we're assuming a single non-conservative force for our problems, right? Kind of keep things, solvable in a sense, okay? And that means that our formula, our, kind of E1 equals E2 has an extra term. Check it out. So this would be the E1 side of the equation that we solved a lot of problems with. This would be the E2 side over here. And the only thing is on the left-hand side of the equation, we've added a term. We've added the work done by non-conservative force. Okay. Now, a lot of people ask me, why do we add it? Shouldn't we be subtracting it? Because, this essentially is the energy we start with, the mechanical energy we start with. And if we're adding the work done by non-conservative force, does that mean that our starting energy is bigger? Shouldn't we subtract it, or shouldn't we add it to the final side to say that we have to have more energy to start with because some of it has to go somewhere? Those are valid points if you're forgetting that the work done by non-conservative energy is always negative by definition. So you have to add it because you're adding a negative. If you were subtracting it, then you would be double counting the negative. You subtract a negative, which is like adding, all right? And then you might ask yourself, or might ask me, right? So you might say, well, why not just subtract the magnitude? Because then we have to remember that we're talking about the magnitude. It's better to just stick with the definition of work rather than introducing extra things. Be like, oh, is this work or is this the magnitude of work? That's confusing. Now, but if we just stick to one rule where we know we always see work and we always know that work is always calculated the same way, the definition of work is force times distance times cosine of the angle between those two vectors, then we're fine, because that will always apply. All right? And that's what applies here. And that means that when we look at the work done by the non-conservative force, it is for the friction vector times the displacement vector, their magnitudes, times cosine of the angle between the two, and the angle between the two is always, always, always 180 degrees. Friction and air resistance, otherwise known as drag, always oppose motion. They always oppose the velocity. That's what they are. And since those are the only type of non-conservative forces that we're going to see, that means this angle is always 180, which means that the work done by non-conservative forces is always less than zero. It's always negative, which is why we have to add it. Okay? All right. Get the point. Let's do some examples. All right? So type 1, simple problems involving only kinetic energy and the work done by friction, and that can also be solved with the work energy theorem. All right? Type 2, fairly complex problems that involve potential energy, gravitational and or elastic, and work done by friction. All right? So those ones couldn't be really easily solved by the work energy principle, because we've got, if we have a spring in there, we can't really express the work done by a spring unless we use an integral, and we don't use calculus in this class. So in that sense, we kind of have to use the whole energy conservation equation, but it's a fine line. All right? But the point is that they're a little bit more complex. Okay? And finally, type 3, fairly complex problems that involve potential energy, gravitational and elastic, and work done by non-conservative forces other than friction. Okay? So that would just be basically drag or air resistance. All right? So let's look at the first one. If a 1,500 kilogram car traveling on flat ground at 18 meters per second slams on its brakes and the friction between its tires in the road caused the car to stop, then how much work did friction do? All right? Well, that's definitely one that we would have seen back in the definition of work chapter, because we could just say, oh, well, it's just work equals kinetic energy. All right? So we could definitely solve that with the work energy principle. If we set it up this way, using our new equation, E1 plus WNC equals E2, then E2 is 0, because the final state, there's no energy. There's no kinetic nor potential. And so then our formula just becomes this, and then we're going to solve for the work done by non-conservative forces, which we see naturally becomes negative, okay, as it should, okay, and then plug in our numbers, and we have negative 240,000 joules, all right? That's how much work friction does, okay? That's how much energy friction removes from the mechanical system, okay? All right, cool. Let's do it again. So this one, I actually forgot to give you a piece of information. When I give you a problem like this, and notice it's very similar to example 1, but now the car is either going downhill or uphill, I have to either give you the friction coefficient if it's a constant slope hill, or I have to give you like the length of the hill. So here, what I should have given you is the length of the hill, because otherwise you don't have enough information to solve it, because it depends. Basically, friction will do more or less work depending on if friction acts really quickly and stops the car really abruptly, or if it stops the car really gradually, okay? And it's just a function of that effect, all right? Because the idea, if we look at the picture here, the car is going downhill. So if you think about it, if friction acts really fast, then there's almost no change in gravitational potential energy, all right? But if friction acts really slowly, then there's actually, the car lost energy, it lost gravitational potential energy, and so then the friction has to deal with that extra loss of gravitational potential energy that then became kinetic energy, right? So there's a real difference here between how the friction is going to act, okay? So with 100 meters, that means it does go a ways downhill, and we're going to use E1 plus the work done by non-conservative forces equals E2. We'll define E2 as 0 again, because since we're saying the bottom of the hill is y equals 0, all right? So then our E1 is the initial kinetic energy. The initial gravitational potential energy is that, mgh. H would just be this height here, okay? And then we have the work done by non-conservative forces, all right? Then we're just going to solve for the work done by non-conservative forces. Notice my H becomes d sine theta, right? Because d is this distance, okay? And so H is just this side of that right triangle, all right? And then we plug in all our values, and we find that in this case, friction does negative 410,000 joules. And notice this was the same car, all right, traveling at the same speed, but the fact that the car was going downhill meant that friction had to do a lot more work, not more negative work, right? It had to remove a lot more energy. And that makes sense, right? Because on the level ground, friction didn't have to deal with the extra kinetic energy that gravity was creating, but on the downward slope to ground, it does have to deal with that extra energy, all right? So that means more work is required from friction. If it was going uphill, it would be less, right? Okay? Because then essentially the hill is helping out friction in terms of getting rid of the kinetic energy, friction is able to do less work. All right, and that's one of the questions I asked in the kind of the follow-up examples. We have the car going uphill, but that time I give you the friction coefficient to mix things up a bit. All right, another example. A block with a mass of 10 kilograms is released from a frictionless ramp. So we got no friction in this part. Okay, 30-degree slope. If you've watched previous lecture videos, you've seen the same problem, but a frictionless one. But now where's the friction come in? It comes in on the ground. So this whole section down here has friction. And it has a friction coefficient, a kinetic friction coefficient of 0.272. Kinetic because the block will already be in motion once it gets down to the ground. All right? If the spring has a spring constant of 1,800 newtons per meter, then in question A, how far will the spring compress? Okay, we can definitely do that. We'll set up our two states, state 1 and state 2. We're going to call those two distances, the 1 meter distance is D, just so we can kind of keep it symbolic and clean for a while and plug in numbers at one step. All right, I always think that's a better way of doing this kind of work. And then here we just have H over D. Oh, there it is. Sine of theta equals H over D. And this will allow us to solve for H in terms of D. Excuse me. Okay. All right, so moving on. We have our energy conservation, right? Just our new form, right? For this lecture, right? It's always going to be E1 plus work NC equals E2. Okay, so what do we know? Well, we know we start with some gravitational potential energy, mgh. We're going to have the friction is going to be d plus x. So d is that fixed distance. We know the friction acts over it. And then x is just going to be the compression distance. Don't worry about that d prime. That's in part B. So x is just going to be this distance here. That's x. Okay? Because friction will continue to act as the spring is compressed. Because after all, it is the same surface. It's not like the friction magically stops acting when it reaches the spring. Now, we could have a change in surface here, and we could define it as such. But I think it's more natural to say, well, this is all the same table, right? If we actually built this thing. And so friction would have to continue the whole way. All right? We have cosine of 180 degrees, which is just going to make this term negative, okay? And then the final energy, E2, is the elastic potential energy of the spring, okay? Because the spring is storing that energy, with the energy that's left over that didn't get converted to heat from friction. All right, so there's our gravity, our initial gravitational energy. Here is the friction doing its work on the 1 meter stretch, which we call D, and here's the friction continuing to do work over the compression distance x, and here is the gravitational stored energy, all right, the elastic stored energy, which I just moved to the left-hand side so I could set the whole thing equal to 0. Why do I want to set the whole thing equal to 0? Well, because we have an x and x squared, and we're solving for x, right? So I want to make this look like, a second-order polynomial, so I can use the quadratic formula, or in this case, I'm just going to plug in all my numbers and then either graph it, use a quadratic formula, or solve it with a polynomial solver, which is built into calculators like Desmos, or you can ask Google to do it, or the Texas Instruments have built-in polynomial solvers. And when we do that, we get a value of 0.14. So the compression distance of the spring is 0.14. And if you consider the same problem with the same block and the same amount of gravitational potential energy when it's frictionless, the compression was, I think, over 30 centimeters. So friction has done a significant amount of work here, but that's because it's a fairly small block, which means it didn't have that much gravitational potential energy, and the friction coefficient is fairly large, okay? Especially for a kinetic friction coefficient. All right, so that's part A, all right? And that one was tricky in a sense because we had to solve for x, where we had an x and an x squared. All right, but what about part 2, or part B, that is? I say here, how far will the block slide back up the incline after the spring pushes it back? Well, okay, so that means, well, what energy are we going to start with? Well, we're going to start with the stored elastic energy, all right? And then friction is going to start doing work again as the block starts to travel back this way. And then we just want to find out, how much energy is left over by the time that all the elastic potential energy is gone and friction has removed its energy of sliding along the flat surface with friction to allow the block to go back uphill. That's the question. How high back up will it go? Okay, well, let's see. All right, so I'm going to go ahead and I put a note here. And notice how the work of non-conservative force makes the order of 1 and 2 matter. What I mean by that is because I even mentioned this when we were dealing with just mechanical energy without friction. And that's the previous lecture, by the way. That would be lecture 14. That when we were doing that, we didn't have to worry about whether we were going from 1 to 2 or 2 to 1 because it was the same. It was totally interchangeable. And that's because the gravity is this thing called path independent. It doesn't matter how you get there; it just matters you get there. The kinetic energy is either going to get converted to gravity, or gravity will get converted to kinetic energy. Just they're totally interchangeable. But once you have friction, they're not, right? Because friction just continues to take away energy. All right, friction did work on the way down. It's going to do work to continue on the way back up. All right, so you can't that you'll see on the final example of this lecture. That means that you can't like skip a point. Because before, remember I said, well, you can, and the best example is a concept question where we went from, point 1 to point 2, or we went from point 2 to point 3, or we just jumped from point 1 to point 3. All right, it was a concept question of dropping the block on the spring. Please refer back to lecture 14 and see the concept question of dropping a block onto a spring and filling in the table of whether the changes in energy were positive or negative. And we could totally just skip over point 2. You can't skip over point 2 when you're doing friction. All right, and so essentially we could call this 3. Right, because really it's actually a different energy state. But I'm kind of calling it 1 because I'm hearkening back to getting back up to some height on the ramp. But it turns out that it never makes it back to the ramp. Let's see, right? And it's kind of cool, because we don't have to assume that. We can just find it out. But I'm getting ahead of myself. Check it out. Okay, so here is the initial stored elastic potential energy. All right, here is the work being done by friction. It's negative, and I'm not showing y this time, but obviously it's because it's cosine 180. All right, and it's going to be d plus x. Okay, we know what x is. We'll use the x we solve for because that is the correct x. The d, I'm assuming it's going to travel the whole distance back up to the ramp. That's the point, right? And then my d prime here is going to represent how high it goes up the ramp. Okay, all right. So then and then d prime is just going to be from this relationship here is just going to be h over sine theta. Okay. Okay. I guess really what I'm doing is I'm solving for h prime because the initial h is this. And so this right here would represent h prime, the new height, right? How far it makes it back up the ramp. Okay, so I set this all up. Don't have to worry about the quadratic formula here because I'm just solving for the one unknown. All right, plug in all my numbers. But I get a negative? What does that mean? I mean, after all, d prime is a distance. A negative distance has no physical meaning. Okay, that's not right. What happened? Did I make an error? No. But there was an assumption that was off, okay? But a negative distance is impossible. So this tells us that the block stops on the flat surface. So I love problems like this where you just say, okay, I'm just going to set something up and solve for it, right? It's totally valid to ask for how high it makes up the ramp. But then I get an answer that makes no physical sense. That's because the question was, yeah, sure, a trick question, but it was a good trick question because it was a valid question to ask. Right? And so this answer, although it doesn't make physical sense, tells us a very direct thing. It tells us that we have to change our conservation of energy equation and don't include any gain in gravitational potential energy, but instead solve for a d prime that is along the flat part. Okay, so what does that look like? All right, so that will just look like this. So this is just the stored elastic energy. Here is friction doing its work. And notice that there's no other term because E2 is 0 now because it's going to stop on the flat ground. So it's not going to have any gravitational potential energy to end with. All right. And so then I'm just going to solve for d prime. And when I go ahead and solve for d prime by plugging in all the numbers, I get 0.55. So that means that it stops somewhere right around here. It makes it about halfway back to the ramp, and that's it. And again, because there's a lot of friction here. And it just come to rest, never to move again. Okay? So that's what's cool about these friction systems is you can kind of continue them until they stop completely, until friction has removed all the mechanical energy from the system. All right, even when there's a back and forth, a storing of energy in the spring in this case. Okay, all right, let's do another one. Here we have the pendulum. All right, so pendulums are great systems for mechanical energy because you can't do Newton's laws with them. I mentioned that before. I think it really highlights one of the utilities of using conservation of energy equations. But pendulums can also have friction. Now we have to be careful with how we're going to do friction. We can't do it in a very realistic way with the pendulum. So instead, I'm just going to say that there is an average force, which is a constant force that's exerted by air drag, and I'm just going to give it a value. So essentially, there's this drag force exerted on the pendulum bob at any given point as it moves in its path. Okay, and that value is always 2.5 newtons. That isn't that realistic. The drag forces are always proportional to velocity, and but we can kind of just simplify it here and say, okay, it's just 2.5 newtons. Okay, so let's set this up. We have 0.1, we have 0.2. The length of the pendulum string is L, and then we got this thing S, which is the arc length. How are we going to find that? Okay, Well, first of all, we're definitely going to start with the same equation. E1 plus the work done by non-conservative forces equals E2. All right, so we start with gravitational potential energy. Here's the friction. It's going to become negative because of that cosine 180. And here's the final energy, which is all kinetic. Okay, and then what's that S? Well, S is the path length, and we can find it as a ratio of the circumference of a circle. All right, so it's the path length. It's also called the arc length because it's a circle. All right, so simply the ratio of 380 over 360 is the same as S over the circumference of 2 pi L, because L is the radius. Right, so that's how you find S. All right. It's a good thing about circles. You can find that path really easily. This is a parabola or something. You're not going to find the path very easily. And it ends up being 1.59 meters. So that's the path that friction acts over, because friction cares not about the vertical distance, but about the overall path. Whereas, of course, gravity only cares about the vertical distance. All right, so then we're just going to solve for V, right? So there's basically our gravitational potential energy. This is the, because this in other words, this part right here would be the answer if there was no friction. But see, then we have to subtract an extra value if there's friction, making the V smaller than it would be otherwise. All right, plug in our numbers, and I'm replacing H with L times 1 minus cosine theta. Again, this is just from setting up a right triangle that looks like this, where the other side here is L minus H. Here, let's do this one more time. So this side is L minus H, and this side is L. All right, there's our theta. And when I do that, I can find out that that's the relationship between H and L. All right, and there we go. 3.06 meters per second. All right, slower than it would be going otherwise, because air resistance, basically air friction, took away energy. Okay, it took away mechanical energy. All right, let's do another one. A roller coaster with a mass of 1,245 kilograms starts with an initial velocity at point A of 1.22 meters per second. All right. It's going to then go down, pick up speed, then go back up to that point. All right. But we find that the speed at point B is only 10 meters per second. That's less than mechanical energy conservation would tell us. That means there had to be some non-conservative force. And I like this, right? Because this is kind of a realistic thing. We could definitely take measurements at these 2 points and then find out, oh, there's some lost energy. And then just account for that lost energy and say, oh, it's got to be, a combination of friction and vibration and air resistance and sound energy and, all these things that are taking away from the perfect mechanical system. All right, so here we'll use the subscripts A and B since they're already in the figure rather than 1 and 2. So EA plus work non-conservative force equals EB. All right, then we're going to just plug in our values here. Okay, this is all the left-hand side. Because the left-hand side, we start with kinetic energy, we start with gravitational energy, and we got our work from non-conservative forces. The right-hand side, we're going to have kinetic energy and gravitational energy as well. So there's actually a lot of non-zero terms here, because at both A and B, there was velocity and gravitational potential. All right, so then I'm going to go ahead and solve for work by non-conservative forces. Again, that's important that it's positive here. It would be negative if I considered, the directionality of the value at any given point. But, when we actually solve for it here, it's going to just naturally be negative because of where we put it. All right, in the conservation of energy equation. Okay, and then simplify it a bit. Right, I just combined all the like terms that I could and plugged in my numbers, and I find that the work from non-conservative forces is negative 121,000 joules. All right, it seems like I keep getting answers on the scale of 10 to the 5, right? It's always 100,000 something. All right, so that's the work done by non-conservative forces. Okay. And then I asked for the average non-conservative force, right? And this is kind of a combination. It's basically the average, because I said, there'd probably be multiple forces contributing to this in the real world. So you could think of this as kind of the average net non-conservative force, okay? In that case, it's just going to be WNC equals FNC times L, right? And then we just solve for that, okay? All right, and when we do, that force should be negative because it should always be pointing in the negative direction relative to basically, positive velocity. And so then we have a force of negative 657.8 newtons. Okay, cool. Pretty straightforward, but definitely just kind of, this is such an iconic type of problem for non-conservative forces to do, to have a coaster here. All right, and notice that I had to give you the path length, and I couldn't have just been clever and say, oh, it's a circle or something, because we have no idea what this curvature is. So it has to be exactly specified what that path length is. In this case, 185 meters. Okay, last one. I'll say, okay, so I'd mentioned this a minute ago as an example. It really highlights not being able to skip a step, unlike we could have with mechanical energy, because we have 3 points. We have point 1, point 2, and point 3. Between point 1 and point 2 is entirely mechanical. There's no friction between points 1 and point 2. But then we're going to have some final velocity that we find based on conservation of mechanical energy at point 2. But then going up the ramp, there is friction. So then we have to find whatever energy is left over at point 2, or is converted at point 2 really, and then find out what happens to it to get up to point 3. All right? So that's the way we have to relate our values in this problem. Right? There's no kind of skipping ahead. Okay? I will mention though that since these there's no curves here, we have like a uniform slope, basically a perfect ramp with only one slope, and then the same thing, a perfect triangular ramp on the other side. That you can actually do this this problem entirely with sum of forces, so Newton's laws, and kinematics. You don't need energy for this problem. I think it's easier with energy, but there's a lot of steps either way. But I've seen students solve this problem entirely with Newton's laws and kinematics. All right. So let's just quickly run through the steps. All right. The problem consists of a truck. There was brake failure, so essentially it's just going to go down this hill and just pick up speed the whole time. The initial hill has an angle of 12 degrees, which is a pretty steep hill. It's got a length of, a distance of 335 meters, so that's our L. All right, we can use that to find H, because we weren't given H, we were given L. Negligible friction. The truck steers the runaway vehicle into the runaway truck ramp. You've probably seen those on freeways. All right, the truck ramp is very steep. It has a slope of 27.9 degrees. That's our beta slope. All right, and by the way, the truck started here V naught at 19.5 meters per second. Obviously, it'll be going faster at point 2 because whatever gravitational potential energy it had will be converted to kinetic energy. All right, and then the truck ramp is a soft sandy surface, so it's got a lot of friction. All right, 0.642. And what is the distance d? The truck moves at the ramp before coming to a stop. All right, so we're trying to solve for d, and we'll need h3 because we'll need to have some gravitational potential energy. Because when the truck goes from point 2 to point 3, it'll be losing mechanical energy to friction, basically converting it to heat, but also it's going to be losing kinetic energy to gravitational energy. Right? That's the good thing about ramps pointing up. It means that friction can do less work. Gravity can share the load. So we're going to have E1 equals E2 equals E3, all right, in terms of energy, all right. So we have potential energy plus kinetic energy. And when I write it this way, I'm acknowledging that this isn't mechanical energy, this is total energy. So there's obviously going to be between E2 and E3, there's going to be plus work done by non-conservative forces. Okay, which I kind of is a little vague in that expression, but in general, of course, the energy is conserved. Okay, all right, and then so this is just between 1 and 2. This will allow us to solve for V2. I'm just going to express V2 symbolically in terms of height 1 and V naught. Okay, and then we're going to go on to finding the energy conservation between E2 and E3. Here you can clearly see that I did put in the work by non-conservative forces, and here is the final energy at point 3. All right, so there we have, there's no potential energy at 2 because this is considered our y equals 0 point. All right, that at the kind of the bottom here. All right, but there's definitely kinetic energy, V2, and we know what the value is. And you could find this numerically. I just wanted to keep it symbolic. All right, and then we have the work done by the friction, all right, with its characteristic cosine 180. And then the final energy is just entirely gravitational because there's no kinetic energy at point 3 because that's, of course, when the truck comes to rest. Okay. And then one thing I want to acknowledge is what does the friction force look like? Because the friction force here is going to be dependent on our sum of forces. We kind of maybe already recognize that of course it's mu k Fn, and since it's sloped, Fn is just mg cosine theta. It's just going to be the cosine component of the full gravitational force, and it's the cosine component because our angle is measured relative to the horizontal. So maybe you just kind of have this memorized or used to it, but here's the full free body diagram to tell us where or what form the friction force takes. And that's the friction force that's going to show up right there. All right, so then I'm going to go ahead and substitute that in. Here I'm just cleaning things up a bit. All right, and then I substitute in the friction force in this step right here. All right, and then I also replaced H3 with d sine beta. So we got a cosine beta from the friction, we got a sine beta from the gravity. All right, we kind of bring it all together, and then we're going to solve for H3. Wait, is that what we're solving for? Yeah, oh, D, we're solving for D actually. That's right, that's why we didn't leave it in terms of H3, because we're solving for this distance. Basically, it tells us how long our runaway ramp has to be, right? So we're going to solve for D. You notice a D shows up here, D shows up here. They're both just D's, there's no D squared or anything because there's no spring. So it's simply a matter of finding that, solving for that D algebraically. Here I'm just doing some steps. The mass cancels out completely. Okay, so that's actually a nice thing here, is because all the ramps are triangular. It's independent of the mass. If we had a curved ramp, then the mass wouldn't cancel out. We saw that with the roller coaster. Okay, is then we have to have an average kind of friction force or average non-conservative force. And then we finally get this nice expression, right? It looks rather complicated, but it did simplify quite a bit if you think about it. It's certainly that it's independent of mass, all right? And it's just we got gravity in here. We've got gravity doesn't cancel because it doesn't show up in one of the terms in the kinetic energy term. We've got the initial velocity. Definitely both the angles show up, and only sine of the first angle shows up because there's no friction on that side. But both sine and cosine of the runaway ramp angle show up, and yeah, and you got your friction coefficient, and it's all in there. All right, and let's plug in our numbers, and we get 114 meters. That's how long a runaway ramp has to be, at least, right? Bare minimum. Okay, for this particular truck moving at that particular speed. Well, really, at that particular speed because the mass doesn't matter. Okay, so there you go. That's really kind of the bigger, kind of a lot of steps side of doing a energy conservation problem, specifically one that involves friction. Okay, all right. Well, thank you so much for watching this video. I hope it's been just a chance to see some extra practice and extra examples of energy conservation. Bye for now.